This speech is about heterogeneous programming on hybrid clusters. First of all, we have to define these objects. Hybrid cluster is a computer built from processors with different architectures. The development of programs for such hybrid cluster is called heterogeneous computing. This work is a part of the project called Developing Supercomputers Based on Russian Hardware, which is carried out in the Institute of System Research, Russian Academy of Sciences. The main purpose of our work is to develop a methodology for optimal and efficient usage of such hybrid clusters. Also, we investigate a set of numerical tasks needed for verification of the methodology and for cross-optimization of the hardware. The first thing which associates with high-performance computing is a top 500 list, so let's briefly explore its evolution during the past several years. Before 2008, everything had been pretty simple. The standard CPUs had dominated in this list. The first non-traditional computer appeared in this list in June 2008, and it was a serious breakthrough. The first petaflop, several times more fast and energy efficient than the previous leader. The experiment was successful and other hybrid supercomputers began to appear. All of them were built with nodes containing a standard multi-core CPU and the different accelerators. The situation had not changed, and we see hybrid computers in top 10, along with classic ones. We can do the following conclusion. Hybrid systems are real, and we shall not hide from them, but learn how to use them efficiently. The brief history of heterogeneous computing starts from IBM Cell processor in 2006, which made a revolution with its energy efficiency and performance. The next step is an introduction of general-purpose GPU chips in 2007 by NVIDIA and advanced microdevices almost at the same time. In 2010, people started to use FPGA chips to build supercomputers. These chips are unbeatable by CPUs and GPUs in a certain set of tasks. In 2012, Intel introduced a new massively parallel architecture, Intel Many Integrated Cores. It's important to mention the new trend, which can be called a tablet PC revolution. While the major market players were developing high-performance massively parallel accelerators, the others started to develop and sell a system on a chip based on ARM RISC architecture and their own proprietary programmable graphic models on board. These chips can be treated as a standard CPU with an integrated mathematical coprocessor. On this summary table, we can see the most popular modern architectures compared by the most important parameters. Its energy efficiency in gigaflops per watt for single and double precision. The orange ones are the most common supercomputer architectures, while the green ones are cheap, $10 or $20 per chip, and several times more effective system-on-a-chip architectures. So, if someone manages to add double precision floating point to such chips, we can get a new revolution in high-performance computing sphere. Here we can see the scheme of typical FAT compute node we have worked with. This configuration can be bought in each shop for about $15,000. Total performance is 10 teraflops in double precision, and the power consumption is 2.7 kW per node. But it's not enough to buy such monster. We should know how to use it properly. It means to achieve maximum possible performance. And there are several problems. In spite of the fact that hybrid chips appeared long ago, there is still no common programming model for these chips. It means that most of developers in most cases don't exactly know how to extract peak possible performance of these powerful processors. In addition, the current situation leaves more questions than answers. Nobody knows which approach will win, but we have to build computers and write software at the moment. On one hand, the development cost is many times higher than hardware cost. On the other, it's unclear how the exaflop class supercomputers will look like and what architectures they will have. And it is unclear how to minimize the risks of choosing the wrong model. At the moment, the following programming models are available. The low-level ones allow to gain a direct control over the device. For the classic architectures, there is an old MPI OpenMP alliance. For the hybrid nodes, there are two alternatives. NVIDIA CUDA, which is a proprietary model and work only with NVIDIA GPUs, and OpenCL, which is the same thing but written in a general way, and OpenCL works on a wide range of hardware from various vendors: NVIDIA, Advanced Microdevices, Intel, IBM, and many more. The high-level models take the work with devices on themselves. They provide task decomposition, load balancing, transfer overlap, and etc. We can mark two groups here: directive-based and command schedulers. The first one is an OpenMP-like approach. We just insert some pragmas into the code, and it is expected that all will work. The problem is that device control is implicit, and we cannot affect the process, for example when low performance is achieved. And the appropriate compilers usually cost money. So we are trying to promote and contribute to the second approach. Here one has to represent a full problem as a set of dependent tasks, or a dependency graph, and the rest is done by scheduler, transfer overlap, load balancing, and etc. All these models are available, but what to do with the old codes? If they don't work on new hardware, there is no need in it. These codes intensively use numerical libraries, which interfaces remained unchanged in years, so the simple usage of new libraries with device manipulation and etc. is just unacceptable. That's why we have to use an additional layer of abstraction, which on one side would have a good old standard interface, and on the other would translate them to the modern proprietary interfaces. After the study of other approaches, we decided to develop a unified infrastructure of heterogeneous computing with our own scheduler, which would combine the following features. First, it should have the simple and lightweight logical model, just several basic operations which would deliver a broad functional when combined together. Then it should provide scalability for all devices on the node and for a distributed system. In addition, it should help to overcome the PCI Express problem and to provide transfer overlap where it is possible. And the last but not the least, the usage of the scheduler should be done through a minimal code. We have implemented the first version of such infrastructure for this specification. It is a common scheduler based on OpenCL model. Now we will briefly discuss the main concepts and review some applications. The main idea is the following. The node is represented as a set of compute units, and each unit is controlled by its own scheduler. Together, all the schedulers form a program for one node, and more widely, for the whole distributed system. In OpenCL, each compute device has its own global memory. So let's define a register as an arbitrary linear region in the global memory of the device. So each device can be split into the topology of registers. Let's define an instruction as an arbitrary compute kernel. Instruction can take registers and control parameters as arguments. In this terminology, each compute device with an OpenCL support can be treated as a computational coprocessor, which can execute instructions on registers. There are several necessary commands that provide data transfer functions. One should be able to transfer an n-dimensional memory regions between host and device, and at the moment n is 1, 2, or 3-dimensional. The lead dimension is required, for example, to process submatrices. These transfers are done by load from host to device registers and store from registers to host commands, which take the ARIA parameters and translate them to the corresponding OpenCL calls. The computational work is done by execution commands, which execute compute kernels written in OpenCL C language. There are two types of arguments for execution command: registers and control parameters, the values of the standard types. The program for the scheduler is a dependency graph consisting of commands of these three types. The command keeps the information about its dependencies and doesn't start before all commands in depend zone become complete. For convenience, commands that use the same registers are automatically dependent. At the moment, the mechanism of dependencies is built over OpenCL events. There are three queues for launching load, store, and execution commands. Execution queue works consequently, so the next command doesn't start before the previous command ends. And other queues work asynchronously, so they can process several transfers at the same time. All three queues work in parallel, so we can get automatic transfer overlap where it is possible. So there is a simple way to use a scheduler. First, one should represent an algorithm as a dependency graph of commands. Then, write computational kernels. This step should be done in any case if one wants to port his code to a hybrid machine. In an ideal situation, this step should take the most time in the whole porting process. It's just left to fill the command queues, arrange the dependencies, and launch the application. Now let's watch some applications of the scheduler. First, the testing machines. We have used the last 3 generations of advanced microdevices graphical chips, last NVIDIA architectures, and Intel and AMD multi-core CPUs. We have worked with supercomputer K100, which has 64 nodes with 2 Intel Xeons and 3 NVIDIA Tesla 2050 GPUs. Also, we launched our applications on a fat node with 8 AMD Radeon 7970 GPUs. When we speak about supercomputing, we remind of high-performance LinPack test. Generally speaking, it computes an LU decomposition of a huge matrix. So as the first test, we decided to do some dense linear algebra and implement a digitref call from LPACK. It is based on 2 BLAS level 3 calls, DGEM and DTRSM. We use the simplest algorithm for DGEM. It can be represented as a small dependency graph. We cut the matrix into blocks, send them one by one to a device, do the computational kernels, and transfer the results back to the host. To work with an arbitrary sized matrices, we use padding, and it slightly lowers the performance. Here is the code which does the DGEM using the scheduler. The commands are dependent by corresponding registers, so all the dependencies will be set automatically. The commanded section, nearly 150 lines, do all the logic. They calculate all parameters of the blocks, padding sizes, matrix offsets, choose kernels, and etc. In a multi-GPU case, we use a data parallel approach. We split the huge matrix into several parts, so each device gets its own submatrix to process. To scale for 8 devices, we use a separate scheduler for each device, and they all do the same algorithm. The results are reasonable. One device works with a kernel performance, which is at 68% of a device peak, and 8 devices are scaled to work with 62 of peak efficiency on big enough matrices. We use the most simple algorithm for LU decomposition, an algorithm without pivoting, to represent the actual workload. The small block is processed on the host, then the corresponding L and U parts are calculated by TRSM call, and the trailing matrix is updated by DGEM. So the concurrent CPU part is a non-accelerated bottleneck of the algorithm. We measure the strong scaling on a fixed size of 100,000 doubles, and when we have 6 or more devices, this CPU part negates all the GPU advantages. If compared to one of the world leaders, the Magma library, we have good scaling and the same level of performance. Here we can see the performance of the most popular modern architectures, Intel Xeon Phi and NVIDIA Kepler. In the recently published results, Magma library scales up to 4 devices, and our scheduler scales up to 6 and 8 devices with a competitive performance. The second model task is a CFD code, a sphere in a supersonic flow. CFD codes are highly resource-consuming. The methods should be extremely accurate, so they use complicated patterns, huge computational domains, unstructured meshes, and lots of time integration steps. We implemented the simplest model task to represent the high workload. The flow is described by Euler equations, the flows through control volumes are calculated with a Roy scheme, and time integration is done by the explicit first-order Runge-Kutta scheme. We use the unstructured hybrid mesh with volumes of different forms. First of all, we implemented computational kernels for these 5 steps in the OpenCL C language and measured their performance on different processors. It's important to mention that the kernel code is the same for all devices. The results are predictable. All kernels here are memory bound, and all the timings correspond to the memory bandwidth ratios. The algorithm for one device is simple. We load data to a device, process it with 5 kernels for the desired number of time steps, and store the result back to host. When we use multiple devices, we should permute the border domains, or halo domains, between corresponding devices. It is done by halo permute call on the CPU. To hide this call behind device computation, we can split the processing of halo volumes and the rest. Here we can see the global dependency graph for an arbitrary number of devices. The same graph works on a distributed system as well. Once again, the accelerations of the consequent algorithm launched on different devices are predictable. They correspond to the memory bandwidth ratios. It's important that all CPUs and GPUs run the same OpenCL C code here. In this table, the GPU to CPU accelerations on the FAT node with 8 AMD Radeons are presented. Roughly speaking, one Radeon 7970 is 4 times faster on these algorithms than the couple of Intel Sandy Bridge CPUs due to memory bandwidth. We see the best speedup on 7 GPUs. It's 20 times out of peak 28 times. Here we can see the efficiency of parallelization on the FAT node. The results are not very good. As we found out, most problems are caused by the unstable AMD drivers. The results on the distributed supercomputer K100 with NVIDIA Tesla C2050 are much better. The strong scaling on meshes with 4 million cells and 16 million cells is good until halo transfers start taking more time than the computations. The performance is more than 90% of peak up to 18 GPUs on 4 million cells and up to 45 GPUs on 16 million cells. A few words about sparse matrix vector multiplications. We implemented kernels which accept matrices in sliced LPAC format and tested them on a standard set of matrices from NVIDIA website. The performance of our kernel is slightly higher just because AMD Radeon has a wider memory bandwidth. At the moment, it's not efficient to do separate calls of SPMV on GPUs. They just can be used as a part of some iterative methods. This is our current research. The results will be presented on the conferences this year. In conclusion, we'd like to say the following. The main problem of modern hybrid clusters is the narrow PCI Express bus. So, as it's spoken here, one of the probable way of future high-performance computing are small hybrid system on a chip. And OpenCL with such common scheduler provide a great way to program these chips. Here is the plan of our investigations and conference participation for this year. Thanks for watching. From Russia with love, Pavel and Anton.